Hey, Algebra 2, hope you're doing well tonight or today or whatever time it is that you're watching this. Maybe the weekend. I don't know. So let's go ahead and get this going. So we are finally on to the guided notes here for CFR3, which is describing transformation of function graphs, transformations, right? So what you did with that pre-work is really what we're going to get at the heart of here. So what we talk about, we got 6 different ways that we can have a transformation, and we're going to start with vertical translations. Now, if you remember back to geometry, translation, or just in general, translation may move something, but it does not change the shape. So it doesn't change the shape, just position. So vertical translation is going to move it up and down. So this is up or down. And this part of translation is changes location, not shape. Changes location, not shape. Now there are other ways that we can change the shape. We'll talk about those as we go through. But right now, what we're going to start with is I want to look at a parent function. I want to do some examples, kind of like we did on that pre-work. Okay, so I'm going to use a PF or a parent function. Yeah, we might as well get some of these down here now. If you see PF, that indicates parent function. And the parent function is just kind of it's the main one that it comes to. It's we start with x squared. That's the quadratic function, and then we can move the quadratic function using the transformations and translations, as well as reflections and compressions and stretches too. But we're going to start with a parent function and describe what happens from there. The beauty of this is that it doesn't matter what function it is. It's still going to behave the same way. If you're uh, if you vertically translate, if you translate up using, or if you translate the quadratic function up, it's going to behave the same way as if you were doing the cube root or the linear or the logarithmic natural log, or just an exponential function. No matter what happens, it does the same thing. It has the same effect on it. But to make it a little more palatable, we're going to use some base parent functions here. I'm going to do an example. I'm just going to do an example here. I'm going to start with f of x is x squared. So in this case, this is my f of x squared. I'm just going to plot it here real quick because I can. And let's see here. Can be a fun one sometimes to graph well. So, oh, that was not what I wanted. Close enough. Okay, so this purple right here is going to represent our base, our parent function of f of x equals x squared. Now, what we're going to do is I've got this f of x. This is my general, again, this is my parent or base function, okay? My parent function here. My parent function is f of x. I'm going to transform that into something new, and I'm going to transform that into, let's go here. How about g of x? And what I'm going to do for vertical translations is I am going to add something or subtract something at the end. So the general form looks like this. G of x equals f of x plus k. And what happens is if k is positive, so if k is greater than 0, or that means k is positive, what happens is the function translates up. So let's say in here, I'm going to move this down a little bit. If k is positive, we translate up. I'm going to move this over a little bit. Whoa, try that again. We translate up. And so what does that look like? So what I'm going to do is this one. I'm going to take this translating up. I'm going to say And it doesn't matter. The g of x is just a way that it doesn't have to be g of x. I'm going to call this new one m of x equals x squared plus 2. Because x squared, and then if I'm adding 2 outside, all it does is translate every point up 2 units. And if I do that, looks a little something like this. Not great, but I do the best I can, right? What happens is it takes x squared and just goes up 2 units, okay? As a general statement, it doesn't matter what function that is. That could have been a square root function or cube root or natural log, any of those functions, it would just move it up 2 units. So in a general sense, this could be like f of x plus 2. This would go up 2 units. Now, conversely, what if k was negative? What if k was less than 0 or k was negative? If k is negative, then we have a translate down. It translates down. Translate down. And what does that look like? Well, I'm glad you asked. What if we had this here? What else do, I don't know, this weird orangish red color. What if we had the function e of x squared minus 3? Because why not? You would take every value from the original parent function and just go down 3. So this would come down to here, down to here, here, here. And it would look like this. It just took, it's the same shape. I mean, as good as I can draw it. It's the same shape, just translated down 3 units. So in general, this could be like the parent function translated down 3 units. Okay, that's the first possible translation or transformation we could have. Okay, now looking at that, let's look at this example. It says identify the parent function from part A and describe the transformation or transformations from the parent function. So there's 2 parts there. So what do you need? You might need the parent functions packet because you might not know what function you're looking for here. Well, here I'm looking at it and I see a of x equals the square root of x minus 4. My parent function is the square root of x. Square root function. Let's do this. The square root function. Fn, we're going to go Fn for function. And if I'm going to describe it, since this is minus 4 at the end, well, I just said that if it's a negative number, if k is less than 0, so if k is negative, this will translate down. So my description is translates down 4 units, or we can just say down 4 units. Okay. That's the first part. I know it might not be the most glamorous in here, but that is our first part. Also, I put a hook on the end of my Radican symbols, so you know that's the end of it. Okay, that'll make more sense later. But all right, so now that we have an understanding of vertical translations up and down, now we need to understand horizontal translations, and that's what's next. All right, so next page, we've got horizontal translations. This is where it gets fun. Well, I think it's all fun, but that's beside the point. That's beside the point. We're going to do the same kind of thing. We're going to take this parent function that we've got, this purple parent function. I'm going to stick with x squared for now. So I'm going to say my example. So my example is still going to be f of x equals x squared. But in a more general sense, we've got this parent function, f of x, and I'm going to leave this here for just a second, my parent function. And we're going to translate it left to right. How we do this, how we do this looks like this. My g of x, my new function, again, this is my new function, or translated function, my new function. This is my parent function, how it translates from this, and how this looks, how this mathematically is written is f of x, we'll go with blue, minus h. You're saying, Mr. Brown, okay, all right. Well, let's just do this real quick. Let's do this real quick. And I've got x squared. Let me just sketch x squared again. We'll go with it. Now, let's say that I wanted to shift it left or right. And hopefully already at this point, you've done the pre-work, because this is going to help out a lot. I'm going to say my m of x, we'll go with, I don't know, this weird brown color. M of x is equal to, we'll go x minus 3 squared. So it's inside of that function. It's inside of what's being done to the function. And if you've done the pre-work, you already know what's happening. This is the opposite of what you think, because in my mind, it's negative. It's minus, right? So it should be shifting left, but it's not. Minus 3 shifts it 3 units right. 1, 2, 3. Now let's see, got one here and here, here and here, and here and here. Close enough. This would shift it 3 units right. So on the inside, if you have x minus a number, if you have x minus a number, it shifts right. It shifts right. And if you don't believe me, plug it into Desmos. If you don't believe me, plug it into Desmos. On the converse, if you have, let's say it was, I don't know, c of x, why not? X plus 5 squared. This would actually shift it 5 units left. So in other words, on the inside, if you have x plus a number, or well, it's the same, right? Because plus you could also represent as minus a negative, or x minus a negative number, and that's why it shifts left. This is a shifts left. It shifts it left. So down here, this is my left. And up here, this is my right. Now it's counterintuitive. I totally understand that that doesn't make a ton of sense. But maybe that's the way that you got to remember, that since it doesn't make sense, then that's the way that it makes sense. Goes the opposite way? I don't know. That's what I'm thinking here. So x plus 5 squared, I would move everything left 5 units. Okay. That is horizontal. And that's why we did the pre-work. That's why we did the pre-work. I wanted you to really see what was going on with that. Okay. So now that we understand how that works on the inside, let's look at this. Let's look at an example question that would contain this. This question says, identify the parent function and describe, it's the wrong one. I copied the wrong one in here. Don't worry about this for now. We're gonna skip this one. We're just gonna go in the second one here. It says, identify the parent function for part A and describe the transformation or transformations from the parent function in part B. We're just looking at number 2 here. Well, if I'm looking here, this says j of x equals, well, they got these vertical bars. If I look back or remember back, that's called absolute value. So this is saying j of x is the absolute value of x plus 3. That's inside the function. Then outside the function is minus 4. My parent function is the absolute value of x, or absolute value. Absolute value function. And my descriptions are this. Well, let's look at the part we learned first. All right, we've got this part on the outside, this minus 4. Notice how this minus 4 is on the outside of the function. That indicates that it's going down or up. In this case, since it's minus 4, it is going down. This indicates down 4 units. Write that down 4 units. And then we just did this x plus 3 or x minus negative 3. This is that counterintuitive. We see plus and we think it should go right. But in this case, it actually goes, well, I'm sorry, this is my right. You think it should go right, but it actually goes left. So this plus 3 in here means it's a translation left. So this plus 3 is 3 units left. So my two descriptions, down 4 units, left 3 units. And if you don't believe me, that's okay. I'm right. Plug it into Desmos and see what happens. Plug it into Desmos and see what happens. All right, that's the first part. We've taken care of our translations. Now we need to take care of stretches and compressions. In other words, like, how do we make it not the same shape? Because none of the stuff we've done so far has changed the shape. It's just moved it around. Just moved around, up, down, left, and right. Now we need to make it skinnier or wider or taller or shorter. We got to see how that works. So let's go ahead and take a look at that. Next page. Vertical stretch or compression. You're going to notice a pattern with vertical things. You'll notice a pattern because we said the up and down translation, the vertical translation, happened outside of the function. Well, just like the vertical translation happens outside of the function, the vertical stretch and compression actually happens outside of the function as well, but it happens a little differently. Let's go with we got our new function, g of x. Again, this is our new function. And this is, we're going to put our parent function. We're going to stick with, we'll stick with x squared. F of x equals x squared for now. And again, this applies to every function. So we've got f of x. And instead of adding or subtracting this time, we're actually going to multiply. So we've got this value on the outside. We're going to call it a. A times f of x. Okay, how does this work? Okay, now let's go ahead and graph. We got to graph our x squared here first, don't we? And again, I'm just pulling these values from the critical points list that we did in the parent functions packet. Okay, this is f of x equals x squared. What if this a value was bigger than 1? What if this a value, so if a was greater than 1, what would happen? So what I'm going to do, let's graph 2x squared. I'm going to graph, I don't know, k of x equals 2x squared. Well, if I double all these values, because it's doubling, it's 2, so I'd square my x's first. So like 0 squared is 0 times 2 is 0. If I have x is 1, 1 squared is 1 times 2 is 2. Oh, I need to do a different color here. Different color here. So this was 2. I've got 0, 0, 1, 2, -1, 2. If I plug 2 in, 2 times 2 is 4, so 2 squared is 4, times 2 is 8, so 2 goes to 8. -2 would also go to 8. And what do we got going on here? Oops, that was not even close. Let's try that again. What has happened here? It's narrower. Oh, I just put this on the wrong line. Hold on. It's narrower, right? It's narrow. We've taken, and in a vertical sense, we've stretched it. If I just, because it's not translating, it's not moving up and down, left or right. I've just taken it, and at my vertex, at this low point, at this 0, 0 point, I'm just stretching it. We call that, if A is greater than 1, a vertical stretch. Vertical stretch. I am taking and stretching it in the vertical sense. It makes it a little taller. Well, this next one's a little bit different. It's not just going to be less than 1. It's not going to be just less than 1. We're going to do a little something different here. We are going to do this. We're going to say if A is between 0 and 1. If A is between 0 and 1. So in other words, you're thinking like a decimal or something like that, right? Or a fraction. I like fractions. This is going to be a vertical compression. Vertical compression. And here's the deal. Like you saw this in the pre-work. You saw this in the pre-work, how instead of stretching it like that would stretch it. If I had a value between 0 and 1, it's actually going to compress it. It's going to make it wider, right? If I squish it down. So it's like taking that and I'm squishing it down and it widens out. Let's do this. How about, let me label this here real quick. This makes it taller. And then I'll go this color. Why not? Oh, I had gray. That's right. I already had gray. Too many colors going on. I've got, how about j of x equals half x squared. Well, what would that do? Well, 0, 0 is still going to be the same thing. Because if I plug 0 in for x, 0 times 0, or 0 squared is 0, times half is 0. Okay, that's all right. Let's just do 2 for a second here. 2 squared is 4, and half of 4 is 2. So 2, 2. -2 would also be 2. And let's do 4, for example. Well, okay, there we go. 4 squared is 16, and half of 16 is 8. So 4 would be 8. -4 would also be 8. You'll notice what's going on here. It's wider, right? It's become wider. I've squished it down, so it's squeezing out the sides, right? So while the vertical stretch was taller, this is going to make it wider. We call that the vertical compression. I know. This is the last one I'm going to do for this part. We're going to do a second part. But I also want to take a look real quick at some examples down here. Okay. And if you're not sure, you can always graph these things. You can always graph these things. Let's look at this parent function. Let's look at the things we know. This +2 is adding way outside the function. We know that's going to go up to. I'm not even looking at the parent function yet. Up 2 units. We know this horizontal because it's inside the function subtracting. Inside the function subtracting, that -4 it's x -4, but it's opposite. It's opposite. This is actually going to go right 4 units. This is going to go right 4. So right 4 units. and we've got half multiplying on the outside. Well, we just kind of saw this example, right? We kind of saw this example. We called when that A value is between 0 and 1, we called that a vertical compression. So that's all we're going to do to describe it right now. This half, that's our new part. We're going to call that our vertical compression. Vertical compression. I'm going to abbreviate that up here by VC. That's going to cause the vertical compression. The one thing we haven't done is talked about what the parent function is, and that's because it doesn't matter. I mean, it does matter because I asked you for it, but it doesn't matter what function it is, it does the same thing. The parent function in this case, I've got the root again, but it's not a square root because it's got this little 3 up here. Well, if you look through your parent function packet, let's see, what's that look like if I got this thing? Oh, it looks a lot like, oh, hold on, let's get there. The cube root function. The parent function here is the cube root function. Cube root function. All right, you're going to do the next one. You're going to do the next one, and then you're going to check it at the beginning of part 2. See you there.